Hi everyone, welcome to this talk of the M2D2 series. Our today's speaker is Tianfan. He is a PhD candidate in computer science at Georgia Tech, supervised by Prof. Jim Maxson. He received his bachelor degree and master degree in computer science from Jiao Tong University, and his research interest lies in developing AI for drug discovery and drug development. Thank you so much, Tianfan, for accepting our invitation um, and looking forward to the talk.
Can I start now?
Yes, thank you.
Okay. Hello, everyone. This is Tianfan Fu from Georgia Tech. Today, I'm delighted to present our recent paper entitled Sample Efficiency Matters, a Benchmark for Practical Molecular Optimization, PMO. It's accepted by NeurIPS dataset and benchmark track recently. This is a joint work with Wenhao Gao from MIT, Professor Jimen Sun from UIUC, and Professor Connor Coley from MIT. And we release our code in GitHub. Molecular discovery is a fundamental problem in multiple scientific disciplines. Concretely, solution to many grand challenges require novel functional molecule. For example, in pharmaceutical science, we are interested in the drug molecules that could bind tightly with the target protein. In material science, we are interested in the material molecule with desired band structure. The process of obtaining novel functional molecule is called molecular discovery. Now we formulate the molecular optimization problem. Molecular discovery is a constrained multiple objective optimization problem. We could formulate it as an optimization problem over the whole molecular space to maximize or minimize the Oracle score. The most widely used method is high throughput screening, but it requires a large number of trial and error and is usually time-consuming and expensive. De novo drug design could potentially accelerate the process, but still lots of problems remain. The first problem is sample efficiency. People usually don't specify the number of Oracle calls, which makes the comparison unfair. For example, only a very few papers report the Oracle calls numbers, and they use different Oracle calls for different methods, which makes it hard to compare this method. The second problem is the selection of oracles. People usually use two trivial oracles, some even self-design. For example, many methods would use QED score to optimize, which is a human curated rules and easy to optimize. Many methods can achieve 0.948, which is estimated to be the global optimum of QED score. Even random scan can reach that scores. So QED score is not a desirable oracle that distinguish multiple methods. Another example is the log-P score, which prefer large benzene rings or carbon atoms. So if you grow the molecule by iteratively add the benzene ring or carbon atom, that log-P score would continue to grow. So it's not also a very trivial oracles. The third problem is experimental report. Different methods have different setup, including training data, starting molecule, different random seed, and hyperparameter tuning strategy. They will also select arbitrary baseline method and report various metrics such as best one, top K, recall, and so on. We expect the ideal algorithm to be powerful, efficient, generalizable, and robust. Concretely, the ideal algorithm should have strong optimization ability and optimize the property within a limited number of oracle calls. Faster the better. Also, we expect the ideal molecular optimization algorithm to achieve decent performance in various tasks and be reasonably robust to random seed. So we design the practical molecular optimization benchmark to meet such requirement. Firstly, we design the metrics to emphasize sample efficiency. We constrain the maximum number of oracle calls to be 10,000. Also, we use the AUC top 10 as a main matrix, which not only considers the top score of the generated molecule, but also considers the sample efficiency. We also cover the most widely used oracles. For example, QED measures the drug likeness, DRD2, JNK3, GSK3 beta measures the binding affinity with a certain target receptor. We also include 19 guacamole oracles, including similarity-based, isomer-based, and so on. Docking score is also an appropriate oracles in our experiment, but it's usually time-consuming to evaluate and still inaccurate, so it's not incorporated in current version. We also want to unify the experiment setup. For example, we want to tune hyperparameter for each method. For each method on each task, we conduct 5 independent runs and report the average performance and their standard deviation. For other methods, we use Sync 215,000 as a database.
I have one question. Before you move, can you go back to the previous slide, please?
Yeah.
So, what's the oracle for DR, D2, and GMK3 and GSK3 beta? Is it just a docking score or the actual binding?
They are not directly docking score, but they are a machine learning that train on the well experiment.
On the binding.
Yeah.
Okay. Okay.
They can
And
be
do you have any
forest or support vector machine.
Okay. Okay, cool. Thank you.
We also observed previous benchmarks are limited in scale. For example, the earliest benchmark is the guacamole, which only consists of 4 machine learning methods, including SMILES LSTM based on hill climbing, Smiley level genetic algorithm, graph level genetic algorithm, and graph level multi-color tree search method. In 2021, therapeutic data command were proposed, which consists of a molecular optimization benchmark that focus on optimized docking score. They include 6 methods, 2 are domain-specific methods, and 4 are state-of-the-art machine learning method. For domain-specific methods, they include high-throughput screening and graph-level genetic algorithm. In machine learning method, they include the LSTM based on hill climbing. GCPN and the MolDQN are both belonging to reinforcement learning method. MARS belonging to MCMC sampling method. Later in 2021, Austin Tripp proposed a new de novo molecular design benchmark, which consists of 3 machine learning methods, including graph-level genetic algorithm, selfies level genetic algorithm, and Gaussian process Bayesian optimization, which makes the genetic algorithm and the Bayesian optimization. In contrast, we cover 25 representative algorithms. There are 2 essential components for a molecular optimization method. The first is a molecular assembly strategy. There are 3 strategies: string-based, graph-based, and synthesis-based. As we all know, there are 2 molecular string representation, SMILES and selfie strings. For graph-based method, condition on the basic building block, we divide them into 2 categories. The first use atom as a basic building block, and the second use a fragment as a building block. Synthesis-based generation method use chemical reaction to construct the molecule. Another aspect is the methodology level. An optimization algorithm can be categorized based on the method they used. For example, genetic algorithm, GA, Monte Carlo tree search, MCTS, Bayesian optimization, BO, variational autoencoder, VAE, generative adversary network, GAN, score-based modeling, SBM, hill climbing, HC, reinforcement learning method, RL, gradient ascent method, GRAD. We totally covered 25 representative algorithms. For some algorithms that is early or with a slow learning process, we don't include them in current version. For example, the BOSS and the Kimball and the game-based method. For all the 25 methods, we conduct the experiment on all the 23 oracles. On each oracle, we conduct 5 independent runs and report the average AUC top 10 scores, which consider not only the top molecule, but also the sample efficiency. We plot all the results in the heat map and rank this method. Here is the overall ranking. For each method, we evaluate 6 metrics. They are AUC top 1, AUC top 10, AUC top 100, and the top 1, top 10, top 100. We average 6 rankings and got the overall ranking. And we rank all the methods by the average ranking. We could draw some conclusion from the experiment study. For example, no method is sample efficiency enough. As shown in these 2 figures, we find most of the methods requires thousands of oracles to get the desirable molecule. We also observed sample efficiency really matters. For example, we highlight 3 hill climbing methods. Their ranking on top K matrix are always higher, but AUC top K matrix always degrade, which means they suffer from poor sampling efficiency and require lots of oracle calls to get the molecule with desirable property. We also find older algorithms are still powerful. For example, reinvent method ranks the first in all the 6 metrics. Another method, selfie reinvent, is simply use selfies to replace smiley strings in reinvent, also ranks the 3rd. Reinvent is a reinforcement learning method which use smiley string as a representation and use a simple recurrent neural network as a generator and train the recurrent neural network with policy gradient. It was proposed in 2017, so it's a relatively old algorithm in this area, but it still performs very well. Another example is genetic algorithm. We find among the top 10 methods, there are 4 genetic algorithm-based methods, which is very surprising and shows that older algorithms are still powerful.
Sorry, Tianfan, there's a question in the chat. Said is asking which graph does the area under the curve accuracy under the curve apply to? Is it the receive operator characteristic, so the rock RUC, or the precision recall, the PR RUC then?
Oh, no, I think it's
so basically what the RUC top 1 and top 10 and top 100 are measuring.
They are the area under the curve is the because we want to measure the sample efficiency, we don't we previous matrix only measures the top K, that is the only measures the top molecule performance, and we also consider this area that's below this curve.
Okay, so basically it's the area under this curve, the top 100 or the top K that the algorithm has found, right?
Yeah.
Okay, cool. There was another question by Songsu. Maybe Songsu and Emmanuel, do you want to open your mic and ask your question yourself, please?
Yeah. I will report the diversity result later. Yeah, it should appear in the next few slides. So I will explain later.
Okay. Then I think there's the question left by Emmanuel. For HC method, do you have an idea about the number of new active that are added at every step during optimization?
Maybe I can clarify my question quickly. So that question was because you were talking about the sample efficiency of hill climbing methods. So I was wondering, like, when you are kind of like generating new compounds and adding them to like kind of fine tune it every time, do you have an idea of like how many new compounds are you adding that are predicted to be active?
I guess it depends. It's a rule of thumb, and in practice, we usually use several hundred of new members each iteration.
Thanks.
Oh. We also compare the selfies and the smiley strings. In this figure, each point represents a comparison where the x-axis represents the smiley's variant performance and the y-axis represents the selfies variant performance. We find that in most cases, the smiley's variant outperforms the selfies, and most of the points are below the dashed lines. An exception is in genetic algorithm, but it's not a head-to-head comparison. So we conclude that Smiley's variance outperforms the selfies variance. People usually have stereotypes that Smiley string suffers from syntax error and a low validity rate. But according to our experiment, we find it does not, and it still performs very well in the experiment.
One question. So the previous figure was showing the validity of each of the optimization algorithm, or it was showing the accuracy, the top one, for example?
We don't report the validity rate because the validity rate for Smiley string is very high, and we think it's already because for other methods such as graph-based method and the synthesis method, the generated molecule are always valid. So we only measure the AUC top K scores.
Okay, so just to clarify my question, is this figure showing the top K or the percentage of valid smile generated and the percentage of valid selfie generated? What is the figure showing? Not clear for me.
It shows a AUC top 10 score.
Top 10, AC top 10. Okay. Okay, cool. Thank you.
We also detect some syntax problem in selfie strings. For example, in these three examples, this is that the selfie string are super long, but it collapses into a very simple molecule because it's not really chemically valid. We also conduct the comparison between model-based method and the model-free method, where each point represents a task, and the x-axis represents the model-free performance, while the y-axis represents the model-based performance. We find that in the high throughput screening scenarios, model-based method can enhance the performance. That is, most of the pink point are above the dash line. This is also validated by the right figures. We find that the red curve would outperform the black curve. While in the other case, such as graph level genetic algorithm and the GFlow net, we find some point are below the dash line and other point are very close to the dash line, which means the model-based method cannot bring the performance gain in these scenarios. So we conclude that we may need better design for model-based method, especially on predictive models. We also study the oracle landscape by doing the hierarchical clustering to the result heat map. We find that similar oracles can be grouped together. For example, the isomer-based oracles and the similarity-based oracles. We also find that different types of landscape are more suitable for different kinds of method. So when we optimize a certain task, we need to first to know which types of oracle landscape it belongs to. It remains an open problem that how to determine the oracle landscape with very limited experimental data set. We also want to emphasize the importance of tuning. We use a reinvent as an example. There are 4 hyperparameters in reinvent. They are experience, replay, learning rate, batch size, and sigmas. We find if we raise the sigma from 100 to 500, the finally performance would increase significantly, while other hyperparameters don't have so much impact on the final performance. And the original sigma value was below 100. So by tuning the number of sigma, we got lots of improvement based on the original implementation. And the sigma is a weight of the oracle score in the learning objective. Increase the sigma means raise the weight of the oracle scores and enhance the optimization ability.
Question? How increasing sigma impact the diversity of the molecule that you generate? And because if the top 100 is all the same molecule, then it's obvious that increasing sigma will improve the accuracy. So how does that impact on the diversity of the molecule?
Yeah, we will mention it later. Actually, optimizing the top K score usually means sacrifice the diversity score.
Okay, thank you.
We also want to mention the importance of repeating multiple trials. For example, as shown in the figures, most of the methods have large variance between the multiple independent trials. So we suggest if you want to got a good performance, you can run it independently multiple times. We also report the SA scores for all the tasks and all the methods. We find some methods have significantly low SA scores, which indicate the generated molecule of this method are easy to be synthesized. For example, the synthesis-based method DocGene CNet, DocGene AE, which are use chemical reaction to grow the molecule so that their molecule would be easy to be synthesized. We also monitor the diversity scores. We find a general trend that the method with strong optimization ability usually suffers from poor diversity score. So we guess maybe the optimization ability sacrifice the diversity score. In real molecule design, we need to make a trade-off between optimization ability and the diversity score. We also release our code in GitHub, and it can run with one line code. For example, in the first line, we want to run the graph level genetic algorithm, and we set it to production mode, which means that we use the default hyperparameters to run the algorithm, and we run the algorithm 10 times independently, and we want to optimize the QED score. In the second line, we want to use the reinvent method. We set it to the tune mode, which means we will explore all the combination of hyperparameter, and for each setup, we run it 5 times independently, and we want to optimize the JNK3 score. And we use the toolkit called WhenDB, which is able to visualize the impact of hyperparameter in an intuitive way. For example, as mentioned in these figures, it's easy to find that the sigma has the largest impact to the performance gain. Finally, we conclude our paper. Firstly, we propose a practical molecule optimization, which is a standard molecule design benchmark, focusing on the sample efficiency as a key impediment to experimental adoption. We investigate 25 methods on 23 objectives to determine the current cutting-edge method, investigate problem, and draw insight for future study. We have the following primary observations. Firstly, method considered to be strong baseline like LSTM-based hill climbing may be inefficiency in data usage. Also, some older methods like reinvent and graph level genetic algorithm outperform the recent method. Also, we find selfies do not seem to offer an immediate benefit in optimization performance compared to smiley string, except in genetic algorithm. Model-based methods have the potential to be more sample efficiency, but require careful design in the inner loop, out loop, and the predictive model. We also observed that overall, different optimization algorithms may excel at different tasks, determined by the landscape of Oracle function. Which algorithm to select is still dependent on the use case and the type of task. Finally, welcome to try our software with one-line code, and our paper is released in preprint in Arxiv. Finally, we want to thank the financial support. Wen Haogao and Professor Conor Colley are supported by the ONR and the Takeda. I and Professor Ji Mensun are supported by several NSF award and NIH award. Thanks for your time.
Perfect. Thank you so much for the presentation, Tianfan. It's time for question. If you have any question, please raise your hand and open your mic for the question. Roy, do you want to go first?
Yeah, sure. Thank you so much for the talk. This is a really interesting talk. I have a question. It's more a general question. It's something that I noticed in the talk, but please do confirm if this is the case. Do you find that with sample efficient molecular optimization, that it really is a function of the molecular representation chosen as well as the corresponding optimization algorithm? And I wrote this in the message. It almost feels like the no free lunch theorem in machine learning. Do you think that's the case that we're observing here?
Sorry, can you repeat your questions?
Oh, sorry. Yeah, I'm saying that. Did you find in your survey that sample efficient molecular optimization is only possible if you choose the right representation for a molecule and the right optimization algorithm? That there's no one representation or one optimization algorithm that works for sample efficient optimization?
Yes, I think so. But generally speaking, it's a case by case studies. So we don't find a algorithm that can handle all the cases.
Okay, yeah, I just wanted to confirm that. Thank you.
Yeah.
I have a question. Okay, maybe. Sangsu, go first, please.
Oh, thank you. Yeah, thank you for the very nice talk. I really like this benchmark. I think this is very important. So I actually have two questions. First of all, I think we need to use theoretical calls for high-parameter tuning because we need to measure the scores. And I know that this is like a big problem in reinforcement learning. And would you have any guidelines for limiting the number of samples that we may use to tune these hyperparameters?
Yes, that's also a great question. Actually, we for all the production and the tuning setup, we use 10,000 oracle calls to either tune the hyperparameter or production. But if you want to tune the hyperparameter with a limited number of oracles, it also works. I think at least based on my experience, at least 2,000 or 3,000 oracles, because if you use for example hundreds of oracles, it's very challenging to find the trend.
Okay, yeah, I see. Thank you very much. So actually, I have another question if we have enough time. So this is more related to the first question about diversity of the optimized molecule. So from my perspective, I think diversity of the optimized molecule is important because we may need to like propose several thousand of molecules to the chemists. And I think that kind of perspective may be already be considered by the top 100 scores. Like, so the point of trying to generate diverse molecules is trying to generate a set of molecules, I think. And we may want to choose a single best molecule from the set of molecules. And I think that is why diversity is important.
Yeah.
Is that the real use case, or is this just simply measured by the top 100 or top 1,000 scoring criterion? So, like,
I think that's a very good question, and yeah, I did see some papers that comprehensively measures diversity and the top K molecules, and yeah, it's for example, we can consider some, for example, product of diversity score and the top K molecule, top K scores as a final matrix.
I see. I'm sorry that I did not make the question more clear. So my question is that if we consider the top K scores, is there any other reason that we should consider the diversity of molecules?
Yeah, I think we still need to consider the diversity score.
I
Hi,
see. Okay.
hello. I'm Wen Hao Gao. I'm also one of the authors in this paper, and I want to comment on your question. So first of all, I think the case is a little bit different. If we are designing small molecules, typically, no one wants to synthesize thousands of molecules in reality, and typically people just pick handful of molecules in that case to synthesize and test them. And at most, the largest number I have seen for small molecular discovery is about 700. So I think over 1,000 is probably biomolecules which can be synthesized with parallel peptide synthesis protocols. So I think it's two different cases. And based on also some comments on the diversity. So I think the most important reason we want to send a batch of molecules to downstream experimental validation is because the current oracles we are using is not perfect. So there are some noise in the oracle, so that we need to try to reduce the failure rate, reduce the false positive rate in our proposal. But eventually what we want is actually just one molecule. So I would say the first requirement for a molecular design algorithm is the optimization ability. And the second requirement, of course, is as long as the oracle are not perfect, is the diversity. So yeah, our paper focused on the optimization ability at this moment, but in reality, especially if we are using the larger noise in our, if there are larger noise in our oracle, we definitely want to include diversity into our consideration.
I see. Okay, thank you so much. I learned a lot. Thank you very much. Yeah.
Thanks.
Perfect. So I have one question, like also on the diversity point. What's the measure of diversity that you've been using? As someone mentioned in the chat, for example, in the different paper, they were talking about like the different mode of the space that they are sampling as the measure of diversity. And also like there's also the diversity, the intrinsic diversity of the top 100 or top 1,000, but also that compared to the best molecule in the training set. Because like in drug discovery, we don't, let's say like all my top 100 are very, very close to the best molecule I know so far. Maybe that's not a lot of information, right? I might not want to sample or to go and synthesize something that's very close to what I already have in my training set, rather something that's a bit more different. So what was the actual measure of diversity that you've been using in the paper?
We use diversity as a tanimoto, the average tanimoto distance between all the molecular pairs. That is 1 minus tanimoto similarity. Similarity is tanimoto similarity is calculated by the Morgan fingerprint, and it's ranging from 0 to 1.
Okay, I see. Thank you. Perfect. Any more question from the audience? If no question, thank you so much.
Sorry, I guess I have a question.
Okay, go ahead.
I guess, you've used GFLnet, so my interest is piqued, but more generally, you've used several fragment-based methods. And my feeling is that fragments were generally designed for like a particular target. So I'm wondering if you've done any adaptation to the tasks in the task set, or if you just used what the methods had as is.
We use a bunch of fragment-based generation method, and so do you mean which task fits the fragment-based generation?
Yeah, I guess that the authors of each of these papers had, one particular target, let's say protein target, when they wrote the paper, and I'm assuming that that influenced their choice of fragments. I'm wondering if, I mean, that's also a weakness of fragment-based methods, I'm fully aware, but I'm wondering if the tasks that you read, the 23 tasks you've picked, are compatible with the fragments that are in those papers.
We don't consider the specific targets, and maybe it's possible to explore the you mean to design the target specific fragment?
Well, not necessarily. I'm just wondering if the evaluation fully makes sense here. But I don't know. I'm maybe not an expert enough in fragments to know if what I'm saying makes sense. I don't know if someone wants to jump in here.
Wenhao, maybe?
Hi, Emmanuel. I think in general for drug design, we are looking at the similar chemical space. So even if the target changes, the fragments are still require the same batch of fragments. And if we are only have a significant change if we change to other applications like material, in that case, fragments library will have a large change. Okay. So in this case, as we are investing in all pharmaceutical related properties, so I don't think the fragment library, if it's specific for a protein target, is a big deal.
Okay, thank you.